Okay, so in today's lecture, we're going to talk about one very important distribution, which is called the normal distribution. Okay, so this is called normal distribution. And then sometimes you will also see people refer this distribution instead of normal as Gaussian distribution. Okay, so this is another name for the same distribution. Okay, so whenever we talk about a distribution, first of all, we will talk about the support or the range for the random variable x. Okay, so this is a distribution that describes some random behavior for x that is in the region from negative infinity to positive infinity. Okay, so this is saying that this value for a random variable x can take any value in this range, and this range is from negative infinity to positive infinity, so cover the real lines. Okay, so that is the support for this random variable x. Okay, and then for this distribution, there are two parameters, just like the gamma distribution. And the two parameters here are the mu, which later we'll talk more about this, and then the mu is also in the range. It can take any real values. And then for the sigma square, is also can take any real value but positive. So here I put a plus at the subscript. You can also see that it's sigma square, so it has to be a positive value. Okay, so this normal distribution or Gaussian distribution has this support and also has two parameters also with those criteria. And now let's define, or let's write down the notation for the normal distribution. So usually we will write x following a normal distribution. We use a capital letter N to denote the normal distribution. And here with two parameters, so we have mu and then the sigma square. Just like how we write down the gamma, we will have alpha and beta. Okay, so similarly, in this notation, we have the x following a normal distribution, and that N is the name of the distribution, and then the mu and the sigma square is the parameters. Okay. After that, we can proceed to the density function. Okay, so the density function for a normal distribution is f of x equal to the following. So it is 1 over 2 pi sigma squared and then square root, and then exponential negative 1 over 2 sigma squared, and then x minus mu squared. So this is since the x is take any continuous value, so this is also a probability density function, since we're talking about continuous random variables. Okay, so here is some basic intros regarding this distribution. So we have the support, and then we know the parameters that we can describe the shape of this the behavior of these random variables, and then we also have the density functions. Okay, and this is one of the most important distribution, I would say, in the whole world, because many nature phenomena are believed that or tend to follow a normal distribution. But that's why the people call it normal, because it's very common in many of the nature phenomena. Okay, so here we can also take a look at the shape for this distribution. So here we have a real line that can cover or that is ranging from negative infinity to positive infinity. And then for the normal distribution, it has a particular shape, which is called a bell shape. Okay. So basically you have a shape that is symmetric from the middle, and then also with a decreasing tail on both sides, and then they are just mirror image, and then they're symmetric. Okay, so now let's see, for a shape that look like this, how does this density function or the parameters is useful in describing a shape that look like this. Okay, so first of all, we can cut this in the middle. So for a normal distribution, if you cut in the middle, this is essentially what the parameter mu is defining. Okay, so once you have a parameter mu, you'll be able to identify or to create some random behavior with the middle part, or later I'll talk about this is essentially the expected value for this random variable. But you will essentially have the center, or the center mass, for example, of this shape located at mu. So you can use mu to pinpoint or shift the way that you want to describe some random behavior. Okay, so for example, you can think of like the average height of a human, and it's very likely that, let's say, I don't know, but maybe you can look up, but let's say it's 170 centimeter. Then you can see that there might be not many people that is very far from this range, and then there are like lots of people centering around in the mean or the expected value. So you can see that this bell shape with the symmetric and then also with the decreasing tail can describe this kind of behavior or many nature phenomena. Okay, and then the mu is one of the important statistics to describe the random behavior here. Okay, so that is one of the parameters here. Okay, so now let's see what does the second parameters mean in this particular distribution. So the second parameter, later I will also talk about some calculation regarding that is called a variance. So essentially the second parameters is to describe the variabilities of these random variables. So here the variance would describe how widely this bell shape will whether it will be very flat or have a very sharp peak. Okay, so let's say if this is, let's say, I'll find some other examples. Maybe I just use height, 170. Okay, maybe there's something. Maybe you can measure the height of some other animals. Maybe for elephants, we can have a higher mean. Okay, but maybe the height of the variance, the height of the elephants have a smaller variance. Okay, then you will observe some random behavior that has this type of shape. Okay, so you can say this is like the height of human. This is the mean of the human, and then the variance, the variabilities of the human, that the height of the human can vary. Okay, but for some other animals, maybe you will have some, let's say, I'll just put other, but you will have a smaller variance. So if you denote this is the human variance, and then this is the sigma of others. Maybe I just use more generic letters. Okay, so mu1, and then sigma square 1, and then mu2, sigma square 2. So in this case, we will have the mu2 is greater in terms of the values because, for example, like some animals can have a larger, a higher weight or higher height. So we will have to describe the distributions for the height of that particular type of animals. Then we will have a larger value for the mean. So mu2 is greater than mu1. However, if most of that species that have a similar height or weight, then we will have a smaller variabilities. So in that case, we will have the sigma 2 square less than the sigma 1 square. So visually, you can see that the variability of the type of this type 2 or some other species here is smaller than the variabilities in the type 1 something in the first category. Yeah. Okay. So mu and the sigma can have this kind of way to describe the behavior of these random behaviors. So you can measure anything. I just made up, let's say, the height or weight. So you can also measure some other, maybe wind speed or some other, like the height of a tree, that kind of things. So yeah, and lots of things that follow this kind of behaviors, where you have a mean that most of the height that follow this mean, that is centered around the mean, but with some variability around that, but you have a very small value or small observations that are too extreme or far from the mean value. Okay, so here we have described the a new distribution, also some support, and then two very important parameters to describe the random behavior. We write x following a normal distribution, and then that's the density function for the normal behavior. And then if you plot this for fixed on the mu, fixed on the sigma, if you plug in different x for the range, you will have this bell shape, or yeah. Any question or comments up to this point for a very basic introduction for this new distribution? Okay, then I would say for the lectures that before midterm 2, we will focusing on some analysis or discussion on this normal distributions. Okay, and then this is the foundation of many other distributions. For example, if you're doing some biological experiments, sometimes you would do a t-test that, for example, you have some data or subjects, and then you apply treatment, and the other group you don't apply treatments, and you want to test whether the mean are significantly different from each other or not, then you probably need to use some t-test to perform that. And then the t-distribution is based on the normal distribution. And later, if we have time, we will talk more about how the normal distribution can develop or progress into a chi-square distribution, and then develop to a t-distribution, and then develop into a f distribution. Okay, so this is the foundation of many important mathematical construct to describe the random behaviors. Okay, any question, comments? Okay, so here, this is called the normal distribution, and then if you have the mean and the sigma square, you can plot or construct or to have a way to describe some random behavior. And sometimes for analysis, people will reduce or to standardize a Gaussian distribution in the following way. And then they will like to transform the data in the following way to facilitate or to simplify the analysis. So if x following a normal distribution with mean mu and sigma square, and then if you perform the following transformation, so let's denote another random variable z, with x minus the mu over the standard deviation, so the sigma without the square. So what you are essentially doing is that you can randomly choose a point, some random behavior in this that follows this distribution, and then if you minus the mean and then standardize or to scaling by 1 over sigma square or divide by 1 over sigma square, you essentially just reshape this bell curve in that has the following effects. Okay, so if you have a general normal distribution with mean mu and sigma square, you do this kind of transformation by shifting all the random variable toward the mean by minus the mean. So you're pulling everything toward the mean, and then you're scaling by the variabilities of these randomness here. You will end up with another distribution, which is called the standard normal distribution. And the standard normal distribution has the following characteristic, is that the mu is equal to 0 and the variability is equal to 1. Okay, so you still have a normal distribution, but the mean is centered around the 0. This is because this transformation is saying that you're dragging all your random variable pulling toward the mean. So the minus the mean have that kind of action to drag everything to the center, and then you will have the center around the zeros. Okay, and then after you scale by the variabilities that coming from a general normal distribution, then you will have a standard normal distribution. So for normal distribution that have mean 0 and variability or variance equal to 1, then this is called the standard normal distribution. Okay. So again, this is a general normal. You can use the mu and the sigma square to visually or also to describe the random behavior for the x here. And then you perform particular standardization, subtracting the mean and then scale by the variabilities, then you will end up with a standard normal distribution. And then sometimes when people calculating, so for example, let's say you are interested in the probability of, let's say, the, let's say the height of a tree, that you know the height of a tree is like 2 meters. And then you're interested in the probability that the trees that is fall in this range from 1.5 meter to 2.5 meter. Now, with the density function, you can just calculate the probability by integrating the density function. So you can integrate from 1.5 meter to 2.5 meter, and then the density function dx. Okay, so if you're able to calculate or to integrate, and also you need to know the variance. Let's say the variance is equal to 0.25. Okay, so the variability of the height of the trees is equal to 0.25, and then you know that on average the tree has a height of 2 meters, and then you're interested in the probability for the trees that has that is fall into this range, then you can easily calculating this integral by plugging in those number to get the probability, which is the area under this curve. So when you have a density function, the area under the curve is referring to the probability, and this is similar to what we did in the very beginning, where we use the integral to calculate the probability of needle intersecting the line. Okay. However, sometimes back in days when they don't have computers, evaluating an integral is extremely difficult. So what do people do is that they first transform the f of x into the standard normal distribution. And then similarly, you will also need to perform the same transformation on the lower bound and the upper bound. Okay, and then you can integrate the corresponding range under the normal distribution. And then here I'm claiming that if you do the same, if you're calculating the integral under the standard normal distribution, you will still get the probability that can answer your original problem. The reason is that when you perform the standardization, all you did is just changing the shape, but it does not alternating the probability of the random behavior. So if you transform the density function into the normal density function, and then if you also transform the range of your interest, you evaluate the integral under the standard normal distribution, it can still answer the problems that we originally have. And what the people did before is that without the computer, they have a pre-calculated table, which is called the Z table. And then you can look up the Z table, and then you can find the probability for the question that is answered under the standard normal distribution. But equivalently, that probability is also the same as the probability in the original problem. So what they did is that they first standardized it into a standard normal, and then they have a dictionary of all the probability under the standard normal distribution. They store those values as dictionary, and then whenever they have the original problem, they will transform into a standard normal distribution problem, and then calculate probability in the simpler case. And then that probability is the same as the original problem. Okay, so that is just a history about some back in days when they don't have computer, and then how they solve this kind of difficult problems. Okay, and then in many of your statistic textbook, in the end at the back of the book, you will see the standard normal table, as well as the T table and then the F table. But that is very useful when you don't have a calculator or when they don't have computer to calculate the probability. But nowadays you have a very powerful cell phone. You can calculate the probability of that very easily on your cell phone. Yeah, but it's just that like 100 years ago, when they don't have computers, they will need to use a dictionary to look up the probability from a standard normal distribution, and then referring back to the question that is in the original domain. Okay, so nowadays for the textbook, you will still see the standard normal distribution. You might wonder, it's very trivial, but just for people without computer, without calculator. So that table is a dictionary. You always look up a dictionary to find out a solution for a arithmetic problem. Okay, any question or comments up to this point? Okay, if not, then let's perform some calculation. Okay. So that was just some history. Okay, so and also if you're because we already have powerful computer nowadays, so you don't need to worry about using the Z table unless you don't have a calculator. Then you can look up that. But we can talk more about those things in some other lab courses. But in this class, it's more for introduction, so I will talk more about focusing more discussion on the normal distribution. And also one more, maybe I'll just provide one more thing for the standard normal density function. So the density function for the standard normal distribution, essentially just plug in the 0 and 1 into the mu and the sigma square. So now you can see that this is the normal distribution for general mu and the sigma square. Okay, and then for the standard normal distribution, you just plug in sigma square equal to 1 and then the mu equal to 0, then you will have the following. And then for this one, by convention, people like to use the letter z. Okay, so we will write the density function in terms of z. So you will have 1 over square root of 2 pi exponential of negative 1/2 z squared. So this is the probability density function for a standard normal distribution. What you did is just plug in sigma squared equal to 1 and mu equal to 0. And here I'm also writing the random variable using the letter z. Okay, that's just convention. Whenever people write standard normal, they like to use z. Okay. And then another thing is that if you are able to, let's say, have a way to sampling from a standard normal distribution, and then if you want to use those samples to describe a more general normal distribution, you can also reverse the transformation in the following way. So here, if z following a standard normal distribution, then if you perform the following transformation, you use mu plus the scaling factor sigma multiplied by z, then x now will follow a normal distribution with the mean mu and the sigma square. Okay, so what we did here is just reverse the process of this transformation. So if you have the z that follows standard normal, if you perform this transformation, you will end up with a new random variable that follow the normal distribution with mean mu and the sigma square. Okay, so this is just a reverse transformation with the mu plus sigma square. Okay, maybe some more history, just if you're interested. But if you're not interested, then feel free to ignore what I'm saying here. So one thing is that sampling from normal. Back in days, sampling from normal is also extremely difficult when they don't have computers. So people come up with many many tricks to sampling from normal. And then, so there's a very difficult way to sample from X. So what people do is that they will come up with many transformation or manipulations or techniques to sample from the standard normal. And then if they want to target a specific normal distribution with mean, mu, and sigma, then they will use that transformation to project onto the actual domain of interest. And also, have you guys heard of variational autoencoder, which is a deep neural network for generating image? Have you guys heard of that? Okay, so one thing is that maybe a decade ago, this is a new model to generating image, like ChatGPT is generating text, and variational autoencoder is a deep neural network to generating image. Okay, and one of the trick that make this variational autoencoder that is trainable, this neural network can be learned, is through that particular trick. Okay, so if you look any of the variational autoencoder for image generation or even for text generation or graph generation, you will always see that formula there. So what the first people who invented the VAE is that they used the neural network to approximate the mu and the sigma squared, and then they sample from the normal, and then they will do that transformation to generating the X. The X can be image, can be text, can be time series, can be graph. Okay, so the trick that allows people to train a neural network like a VAE architecture is through this trick. So this is the key trick that makes the neural network that is trainable. So without that trick, you cannot directly train an encoder decoder framework. So that trick is, so if you look at any of the VAE framework, you will see a encoder. So you have X encode to a latent. This is just history or some comments. If you don't interested, don't worry about it. Okay, and this is called a decoder, and then you have your generated image X. Okay, so training the neural network, you need to train from all the way from back to the beginning. This is called end-to-end training. Okay, but without this trick here, then this neural network is not trainable, so it was stuck in the middle. So what they did, the first guy who invented the VAE framework, is that they proposed this kind of framework. And what they did is that they encode the X into mu and sigma, and then use this transformation to to facilitate the training. Okay, so again, standard normal distribution is a very important distribution in the history, and then it's the foundation of many of the random phenomena and also many of the analysis. And then also this particular trick is the trick that facilitate the image generation neural network. Without that trick, there's no way you can train this framework end to end. So it was stuck in the middle, okay? But this is just some side comments. If you're not interested, then don't worry about it. Yeah. Okay, so before we talk about some other calculations, any comments or thoughts or anything to, any question or comments? Okay, so next, what I want to do is to show the expectation and the second moment and then also the variance for this normal distribution. And again, the thing here is more for a derivation purpose, so you don't need to know about the details if you're not interested. So essentially what I'm going to show is that the E of x equal to mu for the normal distribution, and then the variance of x, which is equal to the second moment minus the square of the first moment equal to the sigma square. So this is the thing that I'm going to show mathematically in the next few next. So, but the details I'm not going to test. Again, this is kind of like the moment generating function. I'm just providing you the derivation. So there's no need to memorize, or if you're not interested, then you don't even need to take notes. This is the result, and I'm just going to show you whether these kind of like verify these results are correct. Okay, but for them, I will using lots of mathematical tricks and some techniques. But if you're not interested, then don't worry about it. It's just for derivation or a presentation purpose. Okay. Okay. So first of all, I'm going to calculating the expectation for the standard normal for the general normal distribution. Okay. So the definition for the expectation again is the integral. So here I'm going to use the definition of the expectation. Okay, which is just x multiplied by f of x dx. Okay, so now this is the definition, and now we're working on a normal distribution. We're going to plug in the density function to replace this f of x. Okay, so we have x multiplied by 1 over 2 pi sigma square exponential of negative 1/2. So there are many ways you can group the things in terms of factor or in the denominator. So here I'm going to group the things in the following way. So x minus mu over sigma. Okay, and then everything squared. So this is the same as the beginning, where usually people put the sigma square in the denominator. But for calculation, I'm going to push the sigma square there into the parenthesis. Okay, so I'm going to write it as a fraction. Okay, so I'm going to write it in this way. Okay, so here what I'm doing is just I'm going to calculate the expectation using the definition. So x multiplied by f of x, that we already know. And now we're just using a new distribution, so I plug in the new density function f of x in that place. Okay. So now we just need to simplify this and check whether it's equal to the mu or not. So that is what we're going to do next. And again, I'm going to use some mathematical tricks, but if it doesn't make sense to you, or then don't worry about it. It's just for demonstration or derivation purpose. Okay. Okay. So here we have an integral that involving x in the front and the x also in the density function. So one trick that we can do here is to do the u substitution. Okay, so what we can do is to set. So here I'm going to use another letter. I'm going to use y to do the substitution. I'm going to use y to denote the things in the fraction form. So I'm going to set y equal to x minus mu over sigma. Okay, so that is saying my x is equal to mu plus sigma multiplied by y. And then dx is equal to sigma dy. Okay, so some standard treatment from the u substitution. You set u, or in this case y, equal to the things that are grouped in the parenthesis. That is saying x is also equal to that, and then dx equal to sigma dy. Okay, 1 second. Yes, yeah, dx equal to sigma dx, dy, yeah. Okay, so standard treatment of the u substitution. Okay, once we have this substitution, let's see what we can do here. We will have minus equal to, and also I'm going to just for notational simplicity, this is from negative infinity to positive infinity, but it's the same throughout the derivation, so I'm not going to write there every time for the range. Okay, so after we notice that x is equal to that, we can write the transformation in the beginning. Okay, and then continue our density function. Okay, so the things that we replace or that we call inside the parentheses square is that we call it y. So right now we just have negative 1/2 y squared. Closing that. Okay, and then we need to replace the dx as well, and then dx after substitution is sigma dy. Okay, so we will have sigma dy. And then if you're interested, so now essentially the integral is with respect to y, but because x is from negative infinity to positive infinity, and then dy is just some transformation that is x minus mu over the sigma, so y also share the support for negative infinity to positive infinity. So again, I'm not going to write down that, but just a common to mention that integral with respect to y, but the y also share the support of negative y equal to negative infinity to y equal to positive infinity. Okay, so this is just a standard treatment of the u substitution. Okay, next I'm going to distribute the things here. Here we have a summation, so a plus b. So I'm going to write it as integral of a and then plus integral of b. Okay, what we have is that, let me put the sigma. Okay. Okay, another comment is that the sigma in the end will cancel out with the sigma square in the denominator. Do you agree with that? Okay, so I'm saying this sigma square in the denominator with a square root will cancel out with this one. Okay, so the sigma square in the denominator and the sigma in the end will be cancelled out. Okay, just sigma over sigma, so it's gone. Okay, so next I'm going to distribute the sum in the beginning. Okay, so first I'm going to write the sigma in the front. Okay, so we have sigma over 2 pi square root of 2 pi, and then we'll have a y from here. Okay, negative 1/2 and then dy. Okay, so what I did here is I'm breaking the sum here And then the first term here only involving the sigma and the y. So the sigma, I put it on the numerator, and the y, I put it on as like a term by itself. Okay, and then the sigma square in the denominator is cancelled out with the last sigma square through the u substitution by construct. Okay, and then this integral also have a second half, so plus a integral for mu over square root of 2 pi negative 1/2 y squared dy. Okay, so again, I'm just separate or distribute the sum of the two terms into two integrals. The first integral involving sigma y, the second integral involving the sigma, the mu. Okay, any question or comments up to this point? Okay, next, I'm going to using some other things that we haven't seen before. Okay, so probably from your other class or some mathematical or a pre-calculus class, you have heard of the function called odd function and even function. Okay, so odd function is function that has this kind of behavior. So f of negative x is equal to negative f of x. There's also another type of function called even function, which have the following behavior, is that negative f of negative x equal to f of x. So one way to think about this is that you can think of it as, for even function, you can have a quadratic function, so center around 0. So if you plug in negative x, when you plug into the quadratic form, you will having this value here. But this value is also the same as when you plug in a positive version of that x. So that is for the even function. And then the odd function, it's like you have like a symmetric or mirror image through the origin. Okay. So when you plug in negative x, is equal to the same when you plug in the positive version of that x, but take the negative sign and then you will bring it back. So on that particular example, when you put the positive part, but you need to take the negative sign to put it back. So that is for odd function. So the right hand side just particular examples to visualize this kind of the definition of the function. Okay, so let me just clear that out. So there's something called even function and odd function that following this kind of behavior or definitions. Okay, so the reason why I introduce these two concepts is the following. So when you integral from the support, or essentially the negative infinity to positive infinity for a odd function, dx, this will equal to 0. Maybe we can use that same example here. So when you integrate for this range, you will have this area and this area. But for the odd function, they will cancel out. So they will result in an integral that equal to 0. And that is one observation that we are going to use here. Okay. So we know that odd function and even function have this kind of characteristic, and then we also know that the integral of an odd function for the whole range is equal to 0. Okay, so now let's go back to our intermediate solution here. So here I'm saying that the y itself So f of y, okay, so here I'm just denoting this part as f of y. Okay, maybe I will put it here. So so here, the y itself is a odd function. So if you plot the y in a on the figure, essentially just from the like the negative or the 45 degree all the way up to the going up, right? So that is a odd function. So this part is the odd function. And then if you plot the exponential -1/2 y squared, you will get very similar to a like a quadratic function or a symmetric that follow the behavior or the definition of the even function. Okay, so this part is essentially an even function. Okay, and now we have the product of an odd function and even function that will give us an odd function. Okay. So now you can see that the first integral is essentially an integral of an odd function. And then, like I said, we know that you integrate with respect to the whole support, it will go to 0 because the bottom part and the part above the line will cancel out, so that the first integral is just reduced to 0. Okay, so you don't need to sometimes you don't need to evaluate the integral. Just through some analysis or some observation, you can easily find out that it's just equal to 0. So this is more of
So, but then I know the second integral just directly follows on from the first one. But the second integral, if you plug, there's only one spot in which you plug in y, and if you plug in y, it's always a positive value, so then the exponent always is negative. Isn't that?
what do you, for the y's you can plug in either positive or negative.
Right.
Yeah.
And so then the end result is that it's e to the power of the negative value. So doesn't that mean it's an even function?
Can you say that again? So your question is whether the second part is even function or not?
Specifically for the second integral,
Oh, the second integral.
Yeah.
Oh, we'll talk more about that later. Let's see. Okay. So maybe, yeah, what was your question regarding the second one, the second line, right?
Yeah.
Okay. Yeah. What was your question?
Now that I'm looking at it again.
That's an even function, right?
Yeah.
The second integral.
Right.
But we only know that the integral of the odd function goes to 0. So we don't know what the behavior of the second one. So we will perform further analysis of that. Yeah. But through observation, the first one will result in an odd function that will easily tells us equal to go to 0. Yeah. So we don't need to evaluate that whole thing at all. We just need to, through observation, we know that's equal to 0 already. Yeah.
Would it be possible for, in the case of that first integral being a even function?
The first one. This one?
No, scroll down. The first integral from
Here.
Will that always be odd, or is there a case where it could be even on the upside
You mean this line here, right?
line below it?
Sorry.
Integral of sigma over 2 pi times y times x.
Oh, this one?
Yes.
Yeah, so that is odd function, right?
Always?
Yeah, because here the y, so f of y equal to y, that's a function, that's an odd function. And then the second part, e of x -1 over 2y squared, that's an even function. Yeah. And then when you multiply an odd function and an even function, it will equal to an odd function, so that's always an odd function.
There's no case where we can construct a random variable where it will change that way.
By what?
There's no instance where we can change the random variable we're evaluating that it would change evaluating this part of it to be even. We can always just assume that once we get to this point, that specific integral is not odd and this started.
Yes, this is more of a by construct part, that we construct an odd function in this way.
Okay.
Yeah, but one thing is that you need to have the function that has this kind of rules. So some of the function that we encounter before may not follow that. The reason is that it's not symmetric around 0. So for example, in the gamma, it's all positive value. So there's no symmetric from the 0. So that does not fulfill the definition of odd and even. So this kind of trick may not.
Sorry, I'm trying to listen to the one.
Yeah.
Can you repeat that?
Yeah. So like I said, when in the previous plot here for this one, so this is essentially f of y equal to y. Okay. So now if you plug in -3, you will have -3. Right. Here, if you plug in 3, you will have a +3. So you plug in the thing that you plug in will be output for the function, right? F of y equal to y. You plug in -3, you will output -3. You plug in +3, you will get a +3. Okay. So for this one, it satisfies the definition of the odd function, right? You plug in -3 into the x, you will have f of -3. That's a +3. Wait a second. Yeah. Yeah. So if you plug in x equal to 3, you will have f of -3. The output for will be, maybe let me write it. So let x equal to 3. Okay. F of -x. So that's a +3. And then make it a -3. This will give you a -3. And then on the right hand side, you will have negative f of x, and the x is a 3. You will have a -3, and then they are equal. So that will fulfill the definition of the odd function. So f of y equal to y is an odd function. Yeah. And maybe we can also visualize the f of y equal to exponential of -1/2 y squared. Okay, so let's say if you plug in y equal to 2, then y squared will be 4, and then you will have negative, and then you will have some value that are located here. If you plug in y equal to -2, that's here, the square will make it positive, and that will essentially give you the same value here. And this will fulfill the definition of the even function. And then, so the first part is the odd function that we already checked by the figure. The second part is also an even function. We also just check with this visualization, and then their product become an odd function. Yeah. So one thing that we need to do is to check their definition, whether they fulfill these two criteria. So the function that we previously encountered, they are working on the support of x equal to 0. So there's no this kind of symmetric or this kind of behavior that we can use odd or even function to characterize them. Yeah. But in this case, in normal distribution, when we talk about support from -infinity to +infinity centered around 0, then we will have this kind of mathematical techniques to describe this behavior. And then once we observe that this is an odd function, then there's even no need to calculating that complicated integral at all. We can just tell it's already zeros. Yeah. But previously, we don't have this kind of odd and even function that's satisfied. So we cannot directly say that's an odd function. Does that answer your question?
Yes, more or less. And it works for any function, including ones that are nonlinear.
As long as check they're odd and even. Yeah. As long as you can check for every x. If these definitions are guaranteed, are satisfied, then you can use this kind of tricks. Yeah. The idea is that the integral for an odd function, so this region and this region will be cancelled out when you evaluate the integral. So that would directly collapse into 0. So there's even no, so I see. So your question could be, it could be very, very other difficult function. But as long as you have a mirror image of that, so let's pretend this part is the same, okay? Then this area, and then it will have something, and then this area, that will have the same area, but it will cancel out to 0. Yeah, so even if you have a very complex function, but as long as you can satisfy for all x, that they are odd function, the area will cancel out to 0. Yeah. So regardless of like how complex or how nonlinear, as long as you can check for every x satisfy that condition, yeah, then that collapse to 0. Yeah. That's it. Yeah. Great question. Yeah. It's okay if I clear up the note. I have a habit of. Yeah. Okay. Yeah. I have a habit of. Yeah. Yeah. Very good discussion. Yeah. So, through observation, then the first part, if you want to directly calculate it, it could be very difficult. But through construct and also by observation, it will just go to 0. There's no need to imagine that. Yeah. Okay, so all we need to do is just to analyzing the behavior of the second integral. Okay, so the second integral here, the one on the top, involving only one y in the middle of this function. There's one more. Okay, so maybe let me put it here. There's one more equalities that we can use. Okay, so let me call this node. Okay, bullet point 1. Okay, let me introduce another equality that we can use. Okay, and this is the integral of an exponential function -1 over x squared, this one, dx. Okay, so this one, it always equal to a constant, and this constant is equal to square root of 2 pi. Okay, so this is another equality that holds. Okay, so like in the earlier when we talk about Poisson distribution, we introduced a equality for the exponential that we can use an infinite sum to replace that. So that is one equality that we can use. We can replace the infinite sum by just e of the x. And then in the binomial distribution, we also introduce another equality that is called a binomial coefficient. This is another equality that holds. So whenever you have this function integrate with respect to -infinity to +infinity, it will always equal to a constant, which is equal to square root of 2 pi. Okay, and again, there's a pi showing up that looks like coming out of nowhere. Okay, but it's just equal to a constant, and then involving pi, similar to our Buffon needle, dropping needles also involving pi's. Okay, and this is another equality that's always true, and then surprisingly also has a pi showing up. Okay, so now I'm going to using that equality to facilitate our computation. Any questions, any comments? Okay, so now let's analyzing the second behavior using this known equality. So what we have here, we will have a constant in the beginning. So we'll have mu over square root of 2 pi, and then integral, which is the same as this part, except that we use the letter y, okay, dy. So we know using this equality, we can replace the integral by square root of 2 pi. Okay, so this will equal to mu. And just to emphasize, what we start from is the expectation of x through the definition. So we started the definition, expectation of x, with the definition x multiplied by f of x. F of x now is a normal density function. We plug in that, and then we use the u substitution to rewrite, or y substitution to write y equal to the thing in the parenthesis. We have the x equal to something, dx equal to something equal to dy, and then we separate the integral into two parts. Through observation, the first part is an odd function. That integral immediately collapses to 0. The second part equal to that. And then we use another equality, is that the integral that of that part equal to square root of 2 pi. Immediately cancel out, equal to mu. So we have shown that the expectation of a normal random variable equal to the mu, which is just the parameter that you use to describe the random behavior, and also visually that is the center mass of that symmetric density function. Any question or comments? Okay, we have about 30 minutes. Let's see if I'm able to. Any question? Or because the other half is more, it's a slightly difficult than this one. Before we proceed, any question, comments? Okay, next I'm going to calculate the second moment, which involving some extensive tricks, okay? Expectation of x squared. So by adding an extra x here, things can get very complicated. Let's see if we have some mathematical tricks to handle that. Okay. Again, through the definition, x squared 1 over 2 pi sigma square square root exponential negative 1/2 x minus mu over sigma square dx. Okay, so this formulation is just different from the previous one by adding one more x in the front, the second moment. Things will get slightly a little bit difficult. Okay. Again, handling this kind of things, let's proceed with the u substitution. Again, I'm going to call my y equal to x minus mu over sigma. Okay? And then we will have x equal to sigma y plus mu. So this part is the same. Dx is equal to sigma dy. Okay. In the beginning, we have an x squared. Okay. So here, let's also adding one more term for x squared. So here we have x equal to a plus b. So x squared is a squared plus b squared plus 2ab. So let's rewrite that. We will have sigma squared y squared plus 2 mu sigma y plus mu squared. Okay. X is equal to a plus b, so x squared is a squared plus b squared plus 2ab, where a is equal to sigma y, b is equal to mu. Okay, so this is just a necessary component for the u substitution. Once you have all the individual components, let's bring it to the picture. Okay. So continue the equal sign integral by replacing the x squared with that term here. Sigma squared y squared plus 2 mu sigma y plus mu squared. Okay. I'm just rewriting the x squared in the way that we reparameterize it. Okay, so that's the x squared part. Now let's continue on the density function part. 1 over 2 pi sigma square, and then don't forget the square root. Okay, exponential negative 1/2. We call the things inside the parenthesis as y, so we have a y square here. And then dx, okay? Dx, it will be replaced by sigma dy. Okay, so this is the new formulation that we have here. The key difference is that instead of x, we have the x squared in the front. So through the u substitution, we have to write the x squared slightly different with 3 terms. So later you will see so previously we have 2 terms, will break into 2 integrals. Now we have 3 terms, it will break into 3 integrals. Okay, you will need to analyzing the behavior of the integrals for each of the component there. And also, as before, the last sigma will cancel out with the sigma square in the denominator. Okay, so this sigma square and this sigma will cancel out. Okay, so in the next line, I'm just not going to write that anymore. So those two will cancel out. Okay, so now let's break the part into 3 different integrals. The first one, sigma square y square 1 over 2 pi dy. Okay, so that's the first one. Plus the second one. So, okay, so let me do maybe I'll do it next line, so I don't I'll show like line by line with more details. Okay, okay, so the second one is just the second term here. I still want to bring the constant in the front, so we will have 2 sigma mu over 2 pi, and then integral of y multiplied by exponential -1/2 y squared dy. Okay, so all I did here is just bring the 2 and the mu and the sigma, and then the 2 pi in the denominator outside the integral because it's a constant. The y itself will be still carried into the integral. So we have the y be inside the integral with the exponential term at the second one. So if you want, you can also do the same for the first one. You can bring whatever constant that does not involving the y to outside. Okay? So this is the second one. We also have a third integral to consider. The third integral is the mu square. Okay, so we have mu square over square root of 2 pi integral of exponential -1/2 y squared dy. Okay, so again, use substitution because of the x squared give us 3 terms. By replacing the x squared, we ends up with 3 integrals. Now we need to analyzing the behavior of the 3 integrals, or more specifically, the function. The function, let's see if we can exploit any of the function definitions to simplify the calculation. Okay, so first of all, I'm claiming that the last integral is just equal to 2 pi, right? That's what we used in the previous equality. The integral of that is just directly equal to 2 pi, square root of 2 pi. It will cancel out. So the last term just equal to mu squared, right? We're just using that equality. The second one, we also already analyzed. So the y is the odd function. The second term is the even function. Okay. So this is odd function. This is even function. Again, this will collapse to 0. So the third term and the second term is easy to analyze, which we already analyzed before. So we're going to use that. So the only tricky part is how to analyzing the behavior of the first integral. Let's see if there's any trick we can do that. Okay, so let me just write down what I said in the next equal sign. So we'll have equal. Let me now bring the constant outside. Have the y squared and then the exponential negative 1/2 y squared dy. Okay, and then the second term, the second integral here, we already analyzed it, is equal to an odd function, so that will collapse into 0. So the second term directly reduced to 0. The third term here, the integral will give us square root of 2 pi, cancel out with that denominator, so it's just plus mu squared. Okay, so the second and the third integral are relatively easy to analyze. All we need to do is just to put some effort on the first integral. Any question up to this point? Okay, so we will do some more tricks on the first one, which is a little bit, will be a little slightly, a little bit complicated. Okay, so the second term and third term, the third integral and second integral already gone, analyzing that. So the trick that we are going to use is that I'm going to call alpha equal to 1/2, okay? I'm just going to denote or define alpha equal to 1/2. I'm going to use a generic letter instead of a constant. Okay, I'm going to call alpha equal to 1/2. And then I'm going to rewrite the integral slightly different, okay? I'm going to write it in this way. Integral. Okay, so instead of the current formulation y squared multiplied by that, I'm going to write it in the following way, okay? So I'm going to write it first with a square bracket. I'm going to introduce a differentiation operation inside the integral, okay? So d with respect to d alpha. Let me first finish the line. Okay, closing the square bracket, dy plus 0 plus mu squared. Okay, again, this is just for showing you the derivation, more of a proof thing. So if it doesn't make sense or if you're not interested, feel free to not take notes or feel free to ignore me. Yeah, but it's just for, if you're interested in some mathematical tricks or how to solve this kind of things, then maybe this is a good review. But I'm not going to test on any of these tricks or these this way to solve difficult problems, but yeah, so feel free to not take notes if you're not interested. Okay, so don't feel yeah, I'm not going to test anything on these. Okay. Okay, so what I did here is that I have rewrite the y squared exponential term by introducing a differentiation operation. Okay, so now I'm claiming the thing that I'm taking derivative, after I'm taking derivative, it will equal to the things that I have on the beginning. Okay, so now let's see. So more of a intuition for the negative, this one, y squared. Okay, so if I take the derivative with respect to alpha this time, I will have the negative sign here in the front, and then e of x, when you take derivative, it's just itself. You will have e of negative alpha y squared. Okay, yeah. D alpha, yeah. So I'm introducing a new operation, the differentiation with respect to alpha, by rewriting the original problem. The original problem is just an integral. The things inside the integral can be slightly difficult. So what we're doing here is that introducing an additional differentiation operation here. Okay, so it's d alpha, yeah. So when you take d alpha of that thing that I write down in the square bracket, here I'm just doing reverse to check if we get the original problem. Okay, so the derivative with respect to alpha, we will have that, and now using the chain rule, we will have another -1 from the chain rule multiplied by y squared. This is equal to exponential negative alpha y squared, and then additional y squared. Okay, so here alpha is equal to 1/2. So if you plug in alpha equal to 1/2, you can see it is equal to the things that we started with. So we can see that the things that I replaced by introducing a differentiation operation is the same as the original problem. So we do not alternate or the quantity here, but we're just introducing a differentiation operation here. Okay. So the things I put in the square bracket is still the same as the original problem. I just rewriting that formulation with a differentiation operation. That's the only thing I did. And the way that I write it is by constructing negative exponential of negative alpha y squared. Okay? So what I'm doing here, the instinct or the intuition here is that I'm writing the same problem in terms of a derivative. So here we have an integral and a derivative. And like we just verified here, the things that I write as the derivative is the same as the original problem. I did not change it because I write it in a different way. Okay.
How is this different from just finding the antiderivative?
Sorry, what? It could be difficult. You have a y square and then you have a that one. You can definitely use other tricks like integration by parts or some other things, but it could be difficult.
Well, isn't that the antiderivative because we're different?
Sorry, which part you were saying the antiderivative?
The negative exponential with the negative alpha y squared.
It's the antiderivative of what?
Of the y squared times exponential.
Yeah. That is just what I did. It's the same thing. I just write it as in the form of derivative.
Okay.
Yeah, they are still the same. Yeah, but later I will manipulate the differentiation thing slightly to ease the computation. Yeah. So here I did not change anything. I just write it different. Okay, so the reason why I want to introduce the derivative here is that here we can change the order. So let's continue on our equal sign here. So we will have, so I'm going to continue work on this one with the differentiation with the square bracket. Okay, so inside we have a constant in the beginning. So sigma square over square root of 2 pi. We also have a -1 from here. This is the -1. I'm going to move it outside. I'm also going to bring the derivative with respect to alpha outside the integral. So the integral is with respect to z, derivative with respect to alpha. So here you can change the order. Let's bring the d and d alpha outside, and then let's continue evaluating on integral on y. So for the y, we will have exponential negative alpha y square dy, and then we have the mu square if you want. So that's coming from the third integral. But the thing we want to evaluate or analyze is this one. So after, yes, yeah.
Where did the negative 1 come from?
Here.
Oh,
This-
right. Okay.
Yeah. So we have a negative sign here. I bring the negative sign outside, bring the d alpha outside. So from the top line and the bottom line, the -1 in the front, derivative outside, and then continue on integral. So now we have an integral of that thing here, which will be slightly easier. Any question up to this point? We have 10 minutes. I think I'm able to finish it. So maybe let me finish the thing and then I will ask question in the end. Okay, so now, again, we just need to analyzing this one that's relatively simpler. Okay, so now I'm going to use, again, our trick is to use the U substitution. I'm going to use Z, okay, another letter to denote okay, so I'm going to use the U substitution trick again, but this trick is also slightly, okay. So I'm going to define my Z as 2 pi multiplied by Y. Okay, and that is saying Y is equal to Z over square root of 2 alpha. dy is equal to 1 over square root of 2 alpha dz. Okay, with these component, let's bring into the picture again. Sigma square over 2 pi, that's the constant in the beginning. And don't forget there's a -1. And then we have our differentiation operation here. And then we have the integral. So the integral will be equal to the following. We'll have 1 over 2 alpha exponential of negative alpha, and then y square is z square over 2 alpha dz. Okay, so what I did here is that the constant in the beginning, the 1 over 2 alpha is coming from the dy dz. Okay, that's the constant. And then inside the exponential term, we have the negative alpha y squared. Y squared through the substitution is z over 2 alpha. And then taking the square is z squared over 2 alpha. Okay. So now we will have the and then you have the third term, the plus mu square. Okay, that's coming from the third integral. Okay, so now continue. We'll have the constant -1 differentiation to alpha exponential negative z square. Okay, let me write in this way. Maybe you will notice what this is. Okay, so through all these tricks, we will simplify the terms in the following. So here, 1 over square root of 2 alpha, for the integral is a constant. So you can bring that outside. Now the integral only going to affect on the exponential of -1/2 z squared. What does that equal to? We have seen again and again today. Square root of 2 pi, right? Yeah. So that's the equality that we have been using. This is the third time we're using that. Okay, so let me write down what I just said. We have that, the alpha, and then let me introducing a bracket just to make things a little bit clear. 2 alpha, and then exponential -1/2 z squared. dz. Okay, so through those tricks, we end up with that term. We already know that thing equal to a constant, which is square root of 2 pi. Okay. Let me finish that. Sigma square root of 2 pi. d alpha 1 over 2 alpha, and then this thing reduced to square root of 2 pi. Okay, so no more integral to worry about. And then in practice, derivative is easier than integral, okay? So you can easily take integral, but you can easily finish calculating a derivative, but it takes time to think about how to solve an integral. Okay, so now there's no more integral to worry about. Let's just focusing on that. Maybe I'll put the negative sign in front, sigma squared over square root of 2 pi. You will have the derivative with respect to alpha, and then inside the squared bracket is this one here, square root of pi over alpha. Okay, so this is just a simple derivative that you can easily calculate it. Okay, so, and also I would just ignore all the plus mu square from the previous that carry over, but I would just don't forget in the end. Okay, so square root of pi over alpha can also be written as square root of pi multiplied by alpha raised to the power of negative 1/2. Okay, so the power of the negative value is that you put it in the denominator. Power of 1/2 is the square root. Okay, I think that's okay. So we're just taking derivative of this part here. So with respect to alpha, then that means the square root of pi is a constant. You will have negative 1/2 alpha negative 3/2. Okay, that's coming from the derivative. Okay, so now that's the final form. All we need to do, just plug in what we define as alpha. In the beginning, we define alpha as the negative, as the 1/2. So all you can do, just plug in alpha, that particular value. Alpha equal to 1/2. That's through the definition. We define alpha equal to 1/2, and then that to construct all those things. Now bring in the 1/2 inside back into our picture. Okay, so the pi will cancel out. So also the negative sign cancel out. And let's see what we have. So we have sigma squared over square root of 2 pi. Have an additional a square root of pi here. When you plug in, okay, so you have a positive copy of 1/2, and then another copy of 1/2 raised to the power of 3/2, and this is equivalent to the power of 2/2 because it's just a power of 1. So when you do the subtraction on the power, that means you only left with a factor, a power of negative 1/2. Okay, I'll just finish before if we have any question. Okay, so we have sigma square root of 2 pi. We have a additional square root of pi, and then 1/2 raised to the power of negative 1/2. And that is just so a fraction okay, so sigma square over 2 pi square root of pi, and then this one will equal to, so let's handle the negative sign, so that will make it 2 to the power of 1/2. Okay, so inside is a fraction, so the negative sign will make a fraction that will make a reciprocal, so 1/1/2, so it's a 2, so 2 raised to the power of 1/2, that's square root of 2, right? So this will be sigma square. Don't forget the final, the things that carry out. Okay, so this is the answer for the second moment. Okay, let me know if you have any question. but all the derivation are correct. Yeah. One more comments. If you do variance equal to second moment minus the square of first moment, sigma square plus mu square minus mu raised to the power of 2 will be sigma square. So the second parameter in this normal distribution is essentially the variance. So we are using the first moment and then the variance to describe the random behavior. Okay, I will pause here. Yeah.